Hello, everyone. My name is Vanamala Venkataswamy. I'm a PhD candidate at the University of Virginia, and I will be presenting our work, RARE, Renewable Energy Aware Resource Management in Data Centers. It's a deep reinforcement learning-based scheduler that we'll be discussing today. So a little bit of background before we jump into the main topic. So job scheduling in green data centers is especially challenging because of the intermittent power supply from renewables, and the renewables can be from multiple sources like wind, solar, and other renewable sources. And this is because the resource pool expands and contracts based on the power supply or the power generation from the renewables. So you can have more resources turned on when there's enough power generation, and you can turn off some resources when there's less power generation. So handling job scheduling in such complex dynamic environment using hand-engineered heuristic scheduling policies can be challenging because it's hard to capture different dynamics with heuristics, and changing the heuristics and repeating the process of testing and tuning could be complicated. So we need smart system software to intelligently manage jobs on available resources. So the motivation for our works come from the limitations of existing work, and some of the limitations are as follows. So the existing work do not address the specific challenges that are present in the green data centers, especially the way the current RL schedulers are designed are basically for traditional data centers with 100% power supply. They do not capture the resource pool expansion and contraction in the state representation. The second challenge or the limitation is the current implementations showcase reinforcement learning schedulers as just black boxes. In that I mean that they just say, okay, reinforcement learning works, but they don't expand on what configurations they used or why the configurations worked or why the RL works at all. And these are some of the references that I'm talking about in terms of limitations. And the third limitation is the RL scheduler design choices are not explored in the existing work. For example, specifically for green data centers, the extended planning horizon matters a lot because the duration of how long we predict, for example, the power generation based on the weather predictions matters. And this is encoded in the state. So the extended planning horizon, the duration of the planning horizon matters a lot. And this is not at all discussed in the existing work. And the existing RL schedulers also overlook the importance of learning and improving from heuristic policies. So there are existing heuristic policies which kind of work, and maybe we can use some of those policies to learn and improve upon with the RL schedulers. So for the rest of the talk, this is the outline. I'll briefly discuss the green data center architecture, the deep reinforcement learning scheduling agent and the training process, and we'll go into evaluation then conclusion. So first, the green data center architecture. So here we have the green data center with some resources, say compute and storage resources, and obviously other resources can be in there. And then this data center is powered by renewable energy sources, and there can be multiple renewable energy sources like wind energy, solar, and we also have energy storage devices or batteries, which can be used as buffers to store excess energy when there's excess generation and to release some of the excess energy when there's less power generation. Additionally, you can have the data center connected to electric grid, which uses brown energy. And this might be necessary when there is absolutely no energy generated from the renewables. And to keep essential infrastructure or critical infrastructure going, we might need to rely on brown energy to some extent, and also probably to meet like really high QoS jobs, we might need to rely on brown energy from time to time. So on the right here is the scheduler, the deep reinforcement learning-based scheduler. And the scheduler takes the state information, and the state information consists of the resources and the jobs. So the jobs arrive in an online fashion, and they first enter into a wait pool, and from the wait pool they get admitted to ready pool. So the DRL scheduler sees the jobs in the ready pool and sees the resources available in the data center, and then makes decisions on what jobs need to be scheduled on what resources. So the first step will be to observe the state, which is the resources and the jobs. And based on the state, the DRL scheduler recommends an action, which is to schedule jobs and the resources. And based on the action, it gets some reward. And the reward functions can be customized based on what your objective is, the scheduling objective is. And then the schedule and the state transitions to new state. So in green data centers, as I mentioned, you can have multiple sources of renewable energies generating power. So here on the left-hand side, we can see that you have two sources of energy, solar and wind. So in a way, so solar and wind energy generations are complementary. Like solar energy generation is maximum during the day, which is like the blue peak here, and the wind energy generation is maximum during the night. So they complement nicely with each other, but we still see that there are periods when we have no energy generation. And even with battery, the red line, although the battery smooths out some of the bumps, we can still see that there are places where we have, no energy generation or less than required energy generation. And the fact is, batteries are expensive, so you could technically have, absolutely 100% covered, but, batteries are expensive. And for a 400 megawatt data center power draw, we would need a battery of 1.3 megawatt size capacity in order to satisfy 100% of power at all the time. And on the right-hand side, we can see similar observations that the power available is not 100% all the time. So we can have like 30% power availability. 30% of the time, you can have 400 kilowatts power available for a data center that draws 400 kilowatt power. So batteries are good, but they're expensive, and so that's not going to be the solution. So we need, again, software that intelligently manages jobs and resources. So now moving on to the deep reinforcement learning scheduling agent. So we train our DRL scheduling agent with custom variant of the actor-critic RL framework. In the interest of time, I will not go into the details of the algorithm. I would recommend you people to look at the paper for more details. So briefly, our agent learns to select jobs from the ready pool that maximizes the total job value with the help of 3 DNNs. The state informations are tuples containing both the resource image and the array of job metadata. Again, the job metadata consists of the job value, QoS, arrival time, and etc. And you can refer to our paper for more information on the metadata. So the agent state information is as follows. So you have one or two, in our case, we represented 2 resource types, CPUs and GPUs. So x-axis represents the number of resources. The y-axis represents the duration for which the job needs to run. So here the duration goes up to 24 hours or time units. So in this picture, we can see that the blue job requires 7 CPU resources, 4 GPU resources for 3 time units, and similarly for red and other colored jobs. And the ready pool consists of the jobs that are ready to be scheduled. And these ready pool is represented by vectors with information for each job is represented, and each job will have like a job ID and the quality of service like 0.9 and resource requirements and other like job arrival time, the time that it needs to run, and etc. And in the bottom here, we can see some of the rows and columns are blacked out. This information is what gives the what specifies the resource availability. So we don't provide the power availability information directly as the state. In turn, we provide that information indirectly as in terms of resource availability. So here we can see at time step 22, there are 70% resources available, 30% not available. And at time step 23, you can see like 80% resources are available and 20% resources are not available because of the way the power is generated. So the data center simulator with a ready pool size of n is converted to an RL state that takes an action index selection from n plus 2 and returns a new state and some reward. So the encoder combines the state information in the resource allocation image along with job metadata array and produces compact vector representation. The resource allocation image is processed by convolutional layers, and the job array is passed through standard feed-forward layers. Again, I would highly recommend to refer to the paper for more details on that. Now, moving on to evaluations. So for the experimental setup, our Green Data Center simulator simulates various workloads using both synthetic and real workloads and various power availability levels from the renewables. Again, the power is both synthetic and real power traces, and it allows for various system and system configurations. The evaluation metric we use is total job value. So the job's value is calculated based on the resources it requested. For example, here, number of CPUs times the unit price for the CPU times the duration for which the job will run, and then plus the number of GPUs, price per unit of GPU, and then duration. So the total job is calculated as a sum of all the job values of the jobs that finished successfully. If the job didn't finish successfully, then its value is discarded. So we specifically chose this metric for the Green Data Center because traditional metrics like utilization would work, but there's no direct way or intuitive way of capturing that because the resource pool expands and contracts. So it's kind of not very clean to capture the utilization of resources. It's not like constant commodity that you can calculate. Similarly, delays, because of the nature of resources going up and down in the Green Data Centers, there are inherently jobs that will get delayed because there are not enough resources available. So we felt that that may not be like a fair enough metric for all the jobs. So total job value is like a monetary equivalent of calculating like the effectiveness of the scheduler in the Green Data Center setting. And then we used some heuristic policies for comparison. For example, shortest job first. Jobs that are shorter get scheduled first, highest quality of service first. So we add quality of service as as part of the job metadata. So the job with highest quality of service will get scheduled first in this scheduling policy. Highest value first. Similarly, the job with highest value will get scheduled first, and the traditional first come first serve scheduling policy. And for the workloads, we used both synthetic and ANL HPC workloads. Synthetic workloads give us more fine-grained control for studying various properties of the scheduler. And we also evaluated with the ANL HPC workloads. And the job distributions for these two workloads are different. For example, synthetic workloads, we had like 70% of the jobs were short jobs with the durations running between 1T to 10T, like 1 time step to 10 time steps. And then another 30% of the jobs were long duration jobs going from 10 to 30 time steps for a 48-hour long simulation period, 48 time step simulation period. And the ANL HPC workloads had majorly large jobs, and there are few smaller jobs in between, but majorly large jobs. So, and also the simulator supports changing the power availability levels. And then we also ran our experiments with both synthetic, which is like controlled power supply, and we have control over how much power supply is going to be data center, and the real power data from Gleam data center at TTU. And so this data is from 2019. So the data consists of 1 year long power generation data from wind and solar energy sources. So I would like to highlight again here that the power is not constant in green data centers. What that means is that based on the energy generated by renewables, the power supply to the data center changes at every time step. So the real data that we collected is for every 15 minutes. The resource pool, based on, again, the power supply, the resource pool expands and contracts at every time step. So this graph shows the performance for synthetic workload. We evaluated for small scale data center, which is between 10 and 50 resources, and a medium scale data center, which has 10 to 300 resources. On the left-hand side, we have small scale data center with up to 50 resources. So the x-axis shows the number of resources, the y-axis shows the evaluation metric, which is the total job value. And for all the resource sizes or data center sizes, we found that DRL scheduler performs better than the heuristic scheduling policies. So it performs 18 to 25% better for small scale data centers. For medium scale data centers, we found that the scheduler performs 2 to 20% better compared to heuristic scheduling policies. And we like to note that as the number of resources increases, as the problem size increases, the performance difference between the DRL scheduler and heuristic policy is not very huge. And this is because the state space increases as the problem size increases. And so the number of states that the reinforcement learning agent has to explore increases. And given the limited episodic values, it cannot look at all the states in order to make like a good decision on what job needs to be scheduled. So that is one of the limitations we found, which we will be looking at later, like how we can scale this for bigger problem sizes. And this graph shows the performance for ANL HPC workload. And for this, we have evaluated only for small cluster size of 10 to 30 resources. Again, on the x-axis, we have number of resources. On y-axis, we have the total job value that we got after evaluating for a set of jobs. Similar to synthetic workload, we found that for 20 to 30 resources, the DRL scheduler performs 7 to 14% better than the heuristic scheduling policies. So here we have evaluated our DRL scheduler with intermittent power supply. So here we are trying to show that the DRL scheduler adapts effectively with changing power supply. So for this experiment, we use synthetic power data. And so 100% power means that the data center has all the power it needs to run the machines. For 90% power, it means that 90% of the times we have 90% power supply, and then 10% of the time we have only 90% of power supply. So it's not constant, like you have 90% of the resources available all the time. There are times, as I mentioned, there are 10% of the times when we randomly turn off 10% of the machines. Similarly, for 80% power supply, we have 20% of the time we randomly turn off 20% of the machines. From the graphs, we can see that both for small scale data center of 50 resources and medium scale data center, DRL scheduler performs better than heuristics policies, and also effectively adapts to the changing power supply situation in the green data center. So for 50 resources, we found DRL performs 8 to 12% better. And for 300 resources, we found that DRL scheduler performs 5 to 20% better than the heuristic policies. Moving on, so this graph shows the performance with extended planning horizon. So as I briefly mentioned earlier, planning horizon dictates how long the scheduler can look ahead in order to plan for what jobs need to be scheduled next. So we know that we have accurate weather prediction and power generation prediction for 24 hours. And with the development of new algorithms and new methods of predicting the weather and the accuracy improves, so we can safely say that in the future we can have prediction windows that are larger, maybe 48, 60, or 72 hours, and with fairly decent accuracy. So this is something that the existing work has completely ignored, as in like a tunable parameter where we can provide information to the scheduler to look ahead and plan when we schedule the jobs. And the heuristic policies by default do not have the ability to look ahead and plan. So they just do maybe a greedy selection of jobs. That's why this experiment is important. And we found that with shorter durations, the DRL scheduler makes myopic decisions, as in it picks the jobs that give maximum value for that fixed amount of time. But when the duration increases from 48, 60 to 72 hours, the DRL scheduler performance increases significantly. So we are showing that with longer planning horizon, the DRL can plan for and therefore get better performance. So on the left-hand side, we show performance improvement for synthetic workloads for 36 to 72 hour time window. And then on the right-hand side, we show similar performance for ANL HPC workloads. So as the planning horizon increases from 36 to 72 hours, the DRL scheduler performs 4% to 14% better than SJF for synthetic workloads, and 6 to 10% better than shortest job first for ANL HPC workloads. And also another point we'd like to highlight is that our colleagues argue that we are limiting the amount of window, but for shortest job first, it does not matter how long or how short the window is. It just greedily picks shortest job first, so it does not matter at all the size of the window. And it does matter significantly for deep reinforcement learning based schedulers. The next evaluation is with varying ready pool size. Again, as I mentioned earlier, one of the challenges is that or limitation with the existing work is that they do not provide an opportunity to change or change the configuration. Earlier in one of the talks, the presenter mentioned that the neural network size is fixed, and that is true. But we need to be able to provide some way of looking at like what can be a good configuration given a specific workload. And here again, we can see from the two graphs, synthetic workload and ANL workload, the performance differences are significantly different because of the way the job distribution changes between the two workloads. On the left-hand side, we show the ready pool size increasing from 5 to 45. So what this means is that the output layers of the scheduler agent can pick between 5 jobs to 45 jobs. And then having this ability to change the network size and configure according to the workload is important. And we see from the figure that the performance difference is significant. So for example, for synthetic workload, the graph on the left-hand side shows that with the ready pool size of 5, we have the total job value around 1 e to the 8. But when we increase the ready pool size to 15, we have a significant performance improvement where we see the performance go to 1.2 e to the 8. So even a slight increase in the performance number can mean, millions of dollars of savings or profits for the data center providers. And further increasing the ready pool size did not increase the performance. And this could be because, for example, in the synthetic workload, the job distribution is almost similar, as in 70% of the jobs are short. So if you give like more jobs to pick from, most of the jobs are similar. So it did not really change the performance significantly, although there is some change between ready pool size of 5 and 25. Similarly, on the right-hand side for ANL workload, when the ready pool size was 5, we had the highest total job value we got, and it didn't improve further. Again, based on, and this is because of the distribution of the workload. Most ANL jobs were large jobs, and giving more options to the scheduler to pick from did not really help because you have like similar jobs coming. So the performance remained consistent. So for synthetic workload, the DRL scheduler performs best at ready pool size of 15 with an 18% improvement over shortest job first. And for ANL workload, DRL scheduler performs 10% better than SJF with a ready pool size of 5 and 7% with a ready pool size of 15 and above. So now moving on to the fourth challenge that we discussed is that the existing systems or the RL schedulers completely ignore the importance of learning from existing heuristic policies. What I mean by that is that if you have existing policies that works well in the environment, you could use or leverage some of those policies to train the DRL scheduler. Here, we train the DRL scheduler by loading the state action information from shortest job first, QoS, HVF, and FCFS. So we preloaded this data while training the DRL, and we evaluated like to what extent the DRL scheduler learns to mimic the policy, and when it did not mimic the policy, how much improvement or what kind of better decisions did it make. So the DRL scheduler had an action agreement of 98% with SJF, 71% of the times it agreed with the quality of service policy, 75% of the time it agreed, the actions picked were agreed with the HVF policy and 80% with the FCFS. The times that the DRL scheduler did not agree or did not pick the same policy as the heuristics, it did actually pick better actions. So the improvement over what we got was is shown in the second row, like 2% over SJF, 5% for QS, 19% improvement compared to HVF, and 7% improvement compared to FCFS. And we are careful in saying that this are exactly what is going to be for different workloads or different scenarios, because a lot of hyperparameter tuning needs to be taken care during this, and we don't want to overtrain. So the percentages are for 10 repetitions, we found this is roughly the same. This percentage improvement remained roughly the same. But we want to further explore this by mixing the heuristic policies into the replay buffer and letting the agent pick from the best policy instead of just one, like SJF or QS. So this is something we will consider in the future. So now moving on to the conclusions. Job scheduling in green data centers is challenging due to the intermittent power supply. So with intermittent power supply, we'll have resources expanding and contracting, and we need smart resource management software that intelligently schedules jobs in such complex dynamic environments. The existing RL schedulers have certain limitations. For example, they do not explore the system design parameters. They treat the RL schedulers as black boxes and ignore the learning and improving from existing heuristic policies. And so in this work, we presented RARE, a unified data center simulator that models the complex green data center with intermittent power supply and allows experimenting with various workloads. We demonstrated that the scheduler performance depends on workloads, and our schedulers must be tuned based on job distributions. We showed that properly configuring the scheduler parameters can lead to significant performance improvements. And we demonstrated that the DRL scheduler can learn and improve from the existing heuristic policies. With that, I'd like to thank you for your time, and I can take questions.
Thank you. We have time for very quick question. Do you think, in your opinion, oh, sorry, I forgot to start my video. Do you think, in your opinion, that people will change their behavior once they learn the intricacies of running data centers based on renewable energy, by means of that when they see that the sun is shining, they will try to submit more jobs?
Well, that is something that we need to buffer. The users, I mean, from experience and discussions, users will not change their applications. They will not change their behavior, but that is something we need to design into the scheduler. So maybe optimize for using maximum renewable energy when it is available, and maybe using brown energy in order to meet user requirements, quality of service requirements.
Yeah, I mean, maybe it's a good idea to use, apart from first come first served, so shortest job first, also some simple heuristic that would do this kind of simple optimization, like energy consuming jobs will be only executed during day because the chance that there will be sun shining is larger, and maybe use this kind of very simple heuristic to actually learn your DLR framework
right.
from. Yeah, I mean, you know what I mean.
Yeah,
It's
yeah,
just,
right.
it's just
I agree. Some of the existing works do talk about deferring the jobs based on, energy available and
yeah.
based on
Okay.
whether the user will agree to delay the jobs. There is existing work on that, but we feel that, that might actually violate the user requirements, for example, quality of service requirements. So, yeah.
Okay. Thank you very much.